All right, so now we're going to talk about what are called nerves. And the basic idea behind nerves are that we're going to look at how sets of, for example, convex sets intersect. And then the intersections are, whether or not they're empty or non-empty, is going to help us define a abstract simplicial complex on that. Okay, so what is the idea of nerves? Okay, so the nerve of a finite collection of sets let's call that collection of sets F, right, consists of all non-empty subcollections where it's like the sets in the subcollection have a non-trivial common intersection, right? Okay, so what that basically is, so the nerve, right, of F is the collection of sort of subsets, if you will, collections of sets, basically, right, where when you intersect things in that set or in that collection, there's a non-trivial intersection. Okay, so X is contained in this collection, all right, with the property that the intersection of X is non-trivial. So perhaps it would be easier to understand. It's like if we drew something, all right. So let's say we have three sets. Okay, let's call them A, B, and C. Okay, so here, right. Actually, maybe let's make life a little bit more interesting and put C here. Okay. So here, what happens is that okay, yeah. So here what's happened is that A and B, it's like have a non-trivial intersection, right? Okay, so the nerve, okay, so if F is this collection of sets, right? A, B, and C, right? Then the nerve of F, okay, is the following. So A and B have a non-trivial intersection, so it's included in this. Okay, so it's a set of sets. Okay, A, B. And then B and C have a non-trivial intersection, so B and C are in there as well. Okay, and then these are the only sort of things with non-trivial intersections. So the nerve of F would just be this sort of collection of sort of sets of sets, if you will. Okay, all right. So hopefully that sort of gives you an idea of what's going on here. Okay, well, maybe let's expand the example a little bit. Let's include D to this. Okay, and then let's say D has a non-trivial intersection with A, B, and D. Okay, so then I would add sort of A, B, D as another term inside this nerve. Okay, all right, so hopefully that gives you an idea of what we're talking about here. Okay, so the point in any case is that this nerve is always an abstract simplicial complex, okay, in the sense that as the appropriate, it's like closedness properties. Okay, so actually, I'm sorry, there's a missing term, right? Because A and D, it's like intersect, have a non-trivial intersection, and B and D have a non-trivial intersection, right? So there's an AD here, and there's there's a BD here. Okay, yeah. All right, okay, so I apologize about that. Okay, so you have, it's like all these terms, right? And so this has a property that it's an abstract simplicial complex, and you recall, it's like one of the properties of an abstract simplicial complex is that if you have a set of sets here, right, then any subset of that set is also in the abstract simplicial complex. So if you have ABD, right, then AB will also be there. It's like, and BD will also be there, right? Okay. And I guess technically speaking, it's like each of those pieces on their own is also part of the simplicial complex. So I apologize. So you also have A on its own, B on its own, C on its own, and D on its own. Okay. All right. So hopefully, yeah, that's what we have, right? So that now it's like would have this property that any set it's like is also, so yeah. Okay. Okay, so you have this abstract simplicial complex. All right. So this is always, the point is that this is always an abstract simplicial complex. Right, irrespective of what is in F. Okay. All right. So again, it's like the whole idea, it's like, if you will, of NERS is that if you have a collection of sets, right, then looking at how these sets intersect, right, give you sort of a structure, it's like, which has the structure of an abstract simplicial complex. Okay. All right. Okay, so the nerve theorem is the following. So, so let's say that F is a finite collection of closed convex sets. In Euclidean space. Okay, then the nerve of F is going to have the same homotopy type as something else. Okay, so then the nerve of F and the union of the sets in F, right, have the same homotopy type. So again, it's like that's sort of the basis. It's like of trying to infer something. It's like about the topology of data. It's like by looking at, again, the intersections of balls. It's like, say, centered around point cloud data. Okay. So I should remark that, like with Halley's theorem, there is a relaxation of the convexity assumption, which is allowed. Okay. So the remark is that as with Halley's theorem, the assumption of convexity can be relaxed. Right. So the relaxation is as follows. If the union of this set F, okay, is triangulable, and then all the sets in F are closed, and all the non-empty common intersections are contractible. and the nerve of F, right, is homotopy equivalent to the union of F. Okay, so so that provides again relaxation which we want. Okay, so in a little bit we'll talk about specific examples, it's like of nerves which come from the intersection of closed balls. Okay, I'll stop here for now.